Okay, hello everyone. I'm gonna do the Special Factorizations and Multivariable Polynomials lecture. So basically the prerequisites is just Simon's favorite factoring trick in factory quadratics. So you just need to know how to factor basic stuff. And then we'll do just 3 topics today. We'll do basic factorizations, advanced factorizations, and multivariable factor theorem. Okay? So let's start with the basics. Also, by the way, I'll be answering questions from the chat if anyone asks. Okay? So basic factorizations, we have two very useful factorizations. Hold on. Okay, so basically we have the sum and difference of squares. It might have been an error, but actually we are just focusing on difference of squares. Okay, so for difference of squares, it's very simple. You just have x squared minus y squared is equal to x plus y times x minus y. This is from your algebra 1 or 2 classes. So it's very simple, but it's very useful. Next, we'll just do this one, which is the sum and difference of cubes. It's a little less known, but it's also very basic. It's just x cubed plus y cubed is equal to x plus y times x squared minus xy plus y squared. If you don't know why these are true, you can just expand the left-hand side and the right-hand side, okay? It's also very similar for the difference. You have x cubed minus y cubed is equal to x minus y times x squared plus xy plus y squared, okay? So as long as you know why these are true, you shouldn't need to memorize these, okay? Okay. So since these are so useful, you can apply these identities to a lot of problems in the AMC and AIME competitions. So let's do some problems. So the first example is very simple. Factor x to the 12 minus 1 over the real numbers. So for most of these examples, I'll be walking you through how to solve it, but I'll also let you have a chance to do the harder problems. Okay, so basically you see this 12 right over here. It's even, so you can factor it as x to the 6 plus 1 times x to the 6 minus 1 first. Okay. Now you have this 6, and you notice that is also a cube. So now you just factor this one as x squared plus 1 times x to the 4th minus x squared plus 1, because you're basically letting y equals x squared, and you're just expanding y cubed plus 1. So that's why we have these x squared and x fourth terms right over here. You can do the same thing, a similar thing for this one. You'll get x squared minus 1 times x to the 4th plus x squared plus 1. It's just, again, this is just sum and difference of cubes. We're basically done here, except we have this unfactored. So we'll bring this over here, and then we have x plus 1 times x minus 1, and then these are all not factorable over the real numbers, as you can see. So we just get the other stuff right over there. So we just copy it. And then we have the last term right over here. X to the 4th plus x squared plus 1. And then this is over the real numbers. So we have our expansion right over here. So this is our complete expansion. Okay? So this is basically a combination of the identities. Let's move on to the next example. So you can try this out. Just think about how to do it. What is the value of 2 plus 3 times 2 squared plus 3 squared all the way up to 2 to the 64? So I'll give you a moment to think about it. It will require us one step. So, okay. Okay, so it's pretty simple. Notice that there's an invisible 1 right here. And then you have these 2, and then 4, 8, 16. These are all powers of 2. So instead, we can just write it, just to make it a bit more clear, as this form. We just switch the 3 squared and the 2 squared. That's all we're doing. And then dot, 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 3 to the 64 plus 2 to the 64. And then now, we can use the difference of squares to collapse this whole thing. So we multiply by 1. And note that 3 minus 2 is 1. So we're just doing nothing to it, except it's just like a clever manipulation. So we can just do it like this. And then dot, 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 right? And then this will be 3 squared minus 2 squared by the difference of squares. And then we also have this term. So we'll bring it down here. Is a plus. And then dot, dot, dot. And then as you can see, it will just keep on collapsing. It will keep on collapsing because these are all powers of 2. And then finally, when we get to 3 to the 64th minus 2 to the 64th, and then we have the last term right over here. So we have this. We will get our final answer, which is just 3 to the 128 minus 2 to the 128. Okay? This might look like an 8, but this is a 2. Okay? So again, this is just, we can collapse a lot of products using difference of squares. Okay. So now let's do the next example. You can also try this one. So it just states let x cubed equals 8x plus y and y cubed equals x plus 8y. If x, the absolute value of x is not equal to the absolute value of y, then find this. Yeah, okay. So just think about that for a second. Okay, so I'm assuming that you've gotten a try at this. So if you're watching this recording on YouTube, you can pause the video. But so I'll just do it. I'll just solve this problem now. So let these two. So you see these cubes. You can actually use the sum of cubes and difference of cubes identities. So we just add these two, and we get x cubed plus y cubed. is equal to 9x plus y. Okay? So now, you can see that this is divisible by x plus y. If you don't see y, I'll just write it out for you. Okay, and then these two cancel because I guess it's non-zero. So x squared minus xy plus y squared is equal to 9. This will be very useful because we can actually now subtract these two equations. So subtracting will give, I'll just do it right over here. So subtracting the second from the first will give x cubed minus y cubed is equal to 8x minus x, so it's just 7x, and then y minus 8y is just negative 7y, so it's just 7 times x minus y. So, and then again, if you don't see this, you can just write it out. xy. And then bam, and then you get this. So now we see why we wrote it as with the xy's, because when we move this expression down over here, we get x squared plus xy plus y squared equals 7. From above, we can just add these two to get, so these xy's cancel out. 2 times x squared plus y squared is 16, and x squared plus y squared is 8. And that is our answer. Okay, so with difference of cubes and sum of cubes, you should always try to find these cubes in order to manipulate expressions to those you need. So like x squared plus y squared. Okay. So this one is a little bit easier, probably. It's just compute the real value of x such that x squared plus x plus 1 times x to the 6 plus x cubed plus 1 equals 10 over x minus 1. As I said, you should always identify like which, are there any significant powers that pop up like 2 and 6. So like the 6 should give you a hint that this will collapse. So actually we can just multiply by x minus 1 on both sides. And then this will give us this. So as you can see, this is not really anything new. There's no polynomial work. Like in the last lecture, is just using these factorizations. So this, if you let x equals x and y equals 1, you will just get this. So x cubed minus 1, because we have this difference of cubes factorization. And as I said, this x to the 6th should also hint you to the right solution. So now you just identify, let y equals x cubed, and then you have the same thing as before. So it's just y cubed minus 1 equals 10, and then just substitute it back. So x to the 9th minus 1 equals 10. We're letting y equals x cubed here. And then adding gives this. And then we have the answer. So the 9th root of 11. So we can use a lot of basic stuff to solve complicated problems. Okay. up to here, are there any questions about these basic factorizations? Okay, so I'm assuming there are no questions. We have two more examples. They're very, very basic, but as you can see, they can solve AMC and AIME problems. So let x equals 4 over this ugly expression. Find x plus 1 to the 48. So give this a try. Again, you should, as a hint, just notice 2, 4, 6, 8, 16. So actually it's 2, 4, 8, 16. So it should give you a hint. Okay, so again, I'm assuming I've gotten a go at it. This is a square root, this is a fourth root, this is an eighth root, and this is a 16th root. So obviously this should remind us of this difference of squares. So instead of just multiplying by this square root of 5 minus 1, you should actually multiply by square root of 5, 16th root of 5 minus 1. So you should just rationalize, it's just basically rationalizing the denominator. So x equals 4 times this, and then we're multiplying by root 16th root of 5. Oops. And then we have the 16th root of 5 plus 1 times 16th root 5 minus 1. As you can see, everything collapses from there. So this is just 8th root of 5, because this is just 5 to the 1/16th, and then just squaring it would be 5 to the 1/8. So it's just equivalent. And then we have another 8th root of 5 plus 1 from this one. So we've tackled this one, and this will just be 4th root of 5 minus 1. And then we have this one. And then this will just be the square root of 5 minus 1. Okay, so this actually all simplifies to the denominator. So I'm talking about the denominator. So the denominator would just be square root of 5 plus 1 times square root of 5 minus 1. And then this is just 5 minus 1 is 4. So actually, all of this would be equivalent to x equals to 4 times this over 4. And then it's just the 16th root of 5 minus 1. And then now we just add 1, which is just 16th root of 5. So x plus 1 is 5 to the 1/16th. And then raising it to the 48th power would give 5 cubed. So the answer to this problem is 125. Okay, so notice that there's a common theme for difference of squares, just like difference of cubes. If they differ by like these powers of 2, then you should think about collapsing it using difference of squares. So like as we saw, we multiply by 3 minus 2 in order to collapse this term, then this term, and then so on. And here we did the same thing except with the 16th root of 5. Okay? Because it just ranges from so 1 over 16th root of 5. Sorry. And then so on. So it's 5 to the negative 1 over 2 to the 4, sorry. So these are all powers of 2. Okay? So let's move on. Last example. Also try this. It's kind of like a number theory problem, but it's not. It's very easy if you use the difference of cubes. So there's a prime number p such that 16p plus 1 is the cube of a positive integer. Find p. So give that a try. So as a hint, so that's a hint. Okay, so anyone got the answer in the chat? Okay. I'll just continue. So the positive integer, so let it be k. Let the positive integer be k. So k cubed equals 16p plus 1. First note that because 16p is even, k is odd. Because even plus 1 is just odd. So k must be odd. Okay? If k is even, then this right-hand side would be even, which is not true. Okay, so what you should do here is just subtract 1 from both sides. And then just use the difference of cubes factorization. So we have k minus 1 times k squared plus k plus 1 equals 16p. Now you just use a little logic here. If k is odd, then k minus 1 is even. So this is even. And then if k is odd, then k squared is odd. And then k is odd, so it's just odd plus 1. And then odds, 2 odds make it even. That's a rule. And then even plus 1 is just odd. And then now look at this right-hand side, because you have this 16, and then p is prime. So p is obviously not equal to 2, because if p is 2, then it would say that 33 is a cube of a positive integer. It's not true. So p is odd. So in order for this to be odd, this must be equal to p. And then this must be equal to 16. So we just match these. And then k minus 1 is 16. And then k is 17. Now we haven't found the value of p yet. So we just substitute this k into k squared plus k plus 1. So p equals k squared plus k plus 1. Substitute 17, you get 307. Okay? So p is 307 and we're done. You could have used modular arithmetic over here. So I'll just write p is 307. So you can verify it by just saying that because k is 17, right? K is 17, that means k is just congruent to 1 mod 16. And then this is also 1 mod 16 because this is a multiple of 16. So you can just verify both sides by using modular arithmetic. Okay, good. Okay, so we are done with this section. Basically, you can just use these 3 factorizations to simplify problems. So these 3 are very useful. In the next 2 sections, we'll talk about more advanced factorizations. Okay. So, okay, let's move on to more advanced stuff. So we have 4 top subtopics. So we have completing the square strategy, difference of squares, difference of powers, sum of odd powers, and Sophie-Germain identity. So this is just actually based on this. So we'll actually first let's introduce what this strategy is. So basically, I think somewhere over here. Okay. This is a little bit of motivation for Sophie-Germain. So this will actually bridge two topics together. So this problem says factor x to the 4th plus 4 into real numbers. Real numbers, okay? So don't overthink this. I'll just solve this problem. So we just use completing the square. This is taught in Algebra 1, but it is a very useful strategy. So basically what you do is you make this a square. You purposely make this thing a square by adding or subtracting a term. So here I would just add 4x squared here. And then now you have to subtract 4x squared because you added it here. So you add then subtract the same thing. It's still this thing. So so we made this a square now. This is a square. So this is just x squared plus 2 squared minus 2x squared. Okay, so does everyone see what's going on? Okay. So now you just use difference of squares. You have 2 squares right over here. So x squared plus 2 minus 2x times x squared plus 2 plus 2x. And you can write this a little bit more neatly as x squared minus 2x plus 2 times x squared plus 2x plus 2. This is actually just a Sophie-Germain identity for x equals 1 and y equals 1. So actually x equals x and y equals 1. But we'll talk about that later. This is a very useful strategy. So you just add and subtract. So add and then subtract the same thing. But you have to make this a square. So that's why it's called completing the square. Okay. So this will tackle a lot of problems with messy expressions like this one. Okay, so this one I'll give you 5 minutes to solve this. It's not as, I'll just give you a hint, it's not as hard as it seems. But yeah, so compute this expression over here. You should have a feeling that because this is on the AIME, it should have a very simple answer. So you should actually be thinking about telescoping here. So I'll give you 5 minutes to solve this. Okay. Okay, so if you guys need more time, please let me know. Yeah, so basically like the answer is not very important, but like the strategy is very important. So think about even if you solve the answer, you should try to figure out how to get there. This will I'll put a little bit of polynomial work also. So here notice that 324 is 18 squared. So 18 squared should remind you of this strategy right over here, because these are all raised to the fourth powers, and fourth powers are always squares. Okay, so by now, most of you should have gotten that, let's say, like, these are all in the same form. Okay, so since these are all in the same form, we can just write it as this function. Is actually a polynomial. So f of n is just n to the fourth plus 18 squared. So this should give you a really big hint to what you're supposed to do. So I'll just dive directly into the solution. So since you have these two squares, you're going to complete the square right over here. So you basically add 36n squared to 18 squared, and then subtract 36n squared because it's the same thing. So you have to add the same thing, subtract the same thing, or else it won't be equal to this thing. Okay. Now we just use it's just a little similar to what we did before. So n squared plus 18 squared minus 6n squared. And then now you can just combine. So you can combine by the difference of squares. Okay. Now I'm going to zoom out. Now the path is very clear now. You just factor this for simplicity, okay? Since I don't want to write all of this out. So n times n minus 6 plus 18. Okay? So this will be the form for every one of these expressions right over here. So what we do is just we look for which terms to cancel. So it's going to be a very long denominator. So now we have so the first term is 10, right? N equals 10. So f of 10 is just 10 times 16 plus 18 times 10 times 4 plus 18. Okay? This is just f of 10. And then I'll just write one more term here. So 22 times 28 plus 18 times 22 times 16 plus 18. If you're wondering how I got these numbers, I'm looking at like a blank piece of paper. So I'm looking at the piece of paper with the numbers on it. So we just multiply until n equals 58, right? So basically 58 times, we just add 6. So it's add 6 is 64. And then plus 18. And then we just subtract 6. So 58 times 52 plus 18. Okay? It's a little hard to see which terms cancel, but when we write the denominator, it will be a lot clearer. So we get n equals 4, right? So here, oopsies. So I'll just actually write the numbers here. So 10, 22, 34, 46, 58. And then 4, 16, 28, 40, and 52. So obviously they differ by 6, which means that we're on the right track. Okay? So I've just copied these numbers from the problem right over here. 10, 22, 34, 4, 16, 28. So now we just write the denominator. So I'll just write 4 more terms here. So 4 times 10 plus 18, and then 4 times, let me see, okay, negative 2 plus 18 times dot 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 dot. We get 52. So 52, we increment by 6. 58 plus 18. And then we get 52 times, what was it, 646 plus 18. Intuitively, you should have noticed that these terms cancel. So we get this, and then somewhere over here this will cancel in the dot dot dots right over here. So this will cancel, all of this will cancel. If you don't see why, you can actually write it out, right? Like all of it out, and then all of these will cancel. So 52 times 46, because it's smaller than these, this will also cancel. And then so we have, and then this will cancel with that. And then we are left with these 2 terms. So now our whole thing is, this is 10, right? And then this will be 3730. Okay? And then we have the answer as 373. So, any questions about this example? Okay. So 373 is the answer. So yeah, this is kind of like a telescoping problem, but it uses the completing the square strategy in these intermediate steps. Okay, so the answer is 373. Okay, so now we will move on to the next few. So we'll first cover Sophie Germain, and then we'll cover the other special factorizations. So as we said, the previous example, so the last 2 examples were completing a square, and this was actually a motivation for Sophie Germain. So the actual identity, Sophie Germain identity, states that for all reals AB, we get a to the 4th plus 4b to the 4th equals a squared plus 2b squared plus 2ab times a squared plus 2b squared minus 2ab. The Sophie Germain identity is named after, I think it was a German mathematician, I forgot. But she discovered this during her work in mathematics. But this is actually very easy to derive. So a to the 4th plus b to the 4b to the 4th. So this is actually just a squared squared and 2b squared squared. So this should actually give you the key to the problem if you were to derive this. if you don't see why, you can just expand it, but I'm just going to go over the derivation. So a to the fourth plus 2ab, I think. Actually, 2a squared b squared. No, sorry. A to the fourth plus 4a squared b squared plus 4b to the fourth is, and then you just subtract 4a squared b squared. Okay? Now this is very straightforward. We just did the last example, so we just make it a square, right? So factored, we'll get a squared plus 2b squared minus, this is just a square too, so many squares here. So a squared plus 2b squared minus 2ab squared, and we have, by difference of squares, the Sophie-Germain identity. I wrote it in reverse order, but it's the same thing. Okay, so this is just completing the square. This is actually very useful for problems. It's not very useful, in general, it's not very useful for AMC and AIME problems. But if you want to factor a number in this, in this form, you should use the Sophie-Germain identity. So like in the next example, we want to find the largest prime divisor of 5 to the fourth plus 4 times 6 to the fourth. Okay? Yeah. So it's very easy to see that this is applicable using Sophie-Germain. So we let a equals 5 and b equals 6. Remember there's a 4 right over here. Okay. So just apply Sophie-Germain. Oops. I should zoom out. Times 5 squared plus 2, 6 squared plus 2 times 5 times 6. Okay, so this is just Sophie-Germain. And then note that 5 squared plus 2 times 6 squared is, this thing is just 97, right? So we can simplify our work here. So 97 minus 60 times 97 plus 60. Since we're subtracting and adding. And then this will give us 37 times 157. And then this is basically the prime factorization, because 37 is prime and 157 is prime. And then this asks for the largest prime divisor. Since 157 is prime, we have the answer as 157. Okay? Right. Let's go on. So completing the squares and Sophie-Germain are very useful for squares. So here, if you see squares, you can think of these two. It won't necessarily work, but these are applicable for squares. Okay, so we'll cover these two middle identities. So I'm running a little bit out of space. So I'll just put it over here. Okay. So we have two identities, two advanced identities. Let's see. Okay, so the first one is basically just the difference of powers, where n is a positive integer. So this will be just that, to the n minus 1 plus, I think it's, okay. So we're basically saying that x minus y is a factor of this expression. Okay. If you don't see why, you can also just divide by this x minus y, and this will be a geometric series. Okay, number 2 is the sum of odd powers. This one's probably a little bit harder to see. Oops, sum of odd powers. So 2n plus 1 and 2n plus 1, because this is always congruent to 1 mod 2. I think I'm also forgetting what this actually is. So x to the 2n minus or plus, I think it's minus. So okay. So I'm just looking at the example. Okay, so I think I got it. Y to the y squared plus dot 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 minus x squared y to the 2n minus 2 plus y to the 2n. This is these two identities. If you don't see y, you can also just expand this whole thing by yourself. So this, just remember that this is only for odd powers. Okay? It does not work for even powers. Okay, so any questions about these two? Okay. Okay, so let's switch colors. Okay. So let's move on. We'll use these two identities to tackle a couple more problems. Okay. So example 4.9. I know this numbering is a little off. That's because I put this into the LaTeX file, and then I put this in the wrong order. So sorry if the number is a little confusing. So it's number theory of factoring. So show that 2 to the 27 plus 3 to the 27 is divisible by 35. Think about that. for a second. Okay, so someone asked, is the first identity, so will the first identity work for even numbers? Yes, it will. It will work for any positive integer. See? It will work if for n equals 1, 2, ... Of course, this will work because x squared minus y squared is just the difference of squares. Actually, any even power will work. However, this only works for odd powers. So because this is always odd, right? Not for odd n. Okay, so I want to make this a little bit more clear. So not for, actually, let's just make this super simple. So works for all n. All n. Because 2n plus 1 is always odd. It's always congruent to 1 mod 2, right? So it works for all n. So you won't need to worry about that. Just remember that it's 2n plus 1. So does that clear it up? Okay, so moving on. As I said, where is it actually? Oh, I think I put it in the wrong order again. But okay, so let's just tackle this one first. Show that this and this plus this is divisible by 35. Okay, so think about that for a sec. Okay. So, what do we do here? Well, there is 27 lurking right over there, and 27 is odd. So we can use the odd power identity, I guess. So you might say that you can factor it like that, and then there's something. This is and then it starts with 2 to the 26, and then minus ... You could do that, but the problem is that this sums to 5. And then now you would have to show that this ugly thing is divisible by 7. So you must show that this is divisible by 7. And this I don't know how you would really do that. It's just really hard. You could use some mod arithmetic bash, but it's not going to work out like that. So instead, you would want to know that 2 cubed plus 3 cubed is 8 plus 27 is 35. And then bingo, we have it. So instead, we just use the different one. So we can say that 2 cubed to the 9th plus 3 cubed to the 9th. In other words, I'm just saying that this would be 8 to the 9th plus 27 to the 9th. And then now we can factor it properly, okay? So 8 plus 27 times 8 to the 8 minus 8 to the 6th times 27 squared. And then all of that stuff. And then finally we have plus 27 to the 8th. Note that we are letting n equals 9 here. Sorry. 2n. Yeah, so 2n plus 1. Here is 2n plus 1 is odd, right? It's always odd. So here we would have n equals 4. So this is just the n equals 4 case. Now we just have 35 times all of this big mess right over here. But this big mess is always positive. So we, even if it's negative, we can conclude that our original expression is divisible by 35. So hence, we have proved the original statement. Okay? Because we have this 35 right over here. So this is just sum of our powers. Okay, now let's move on to the second example. So let n be a positive integer. Show that x minus 1 squared is a factor of x to the n minus n times x minus 1 minus 1. This should actually be kind of trivial because you have all these x minus 1s here. So think about that for a second. Okay, so it's very trivial. We rewrite this as x to the n minus 1 minus n times x minus 1. And then you see this is just the difference of powers. This works for n even or odd. So don't worry about the parity right over here. So we can factor it as x minus 1 times x to the n minus 1 plus x to the n minus 2 plus dot 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 plus x plus 1 minus n times x minus 1. And then we can factor an x minus 1 out of this whole thing, which gives us x minus 1 times x to the n minus 1 plus x to the n minus 2 plus dot 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 plus x plus 1 minus n. This n right up here might trick you a little bit, but actually we can do a very clever manipulation. Does anyone have an idea of what this manipulation is? Okay, it's fine. So the manipulation about this n just notice that there are n terms here, right? We have x to the 0, we write this as x to the 0, x to the 1, x to the s squared, all the way to x to the n minus 2 and x to the n minus 1. And you see, if we increment everything by 1, there are n terms here. So in fact, we can actually distribute a 1 to each of these terms, because minus n is just minus n times 1. There are just n ones here, okay? Now we just get x minus 1 times, oopsies, x to the n minus 1 minus 1 plus x to the n minus 2 minus 1 plus dot 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 to x minus 1 plus 1 minus 1. And then don't worry about this because this is 0. So this cancels out. And then all of this is obviously divisible by x minus 1. So we have, so this is divisible by x minus 1 because there's an invisible n minus 1 over here. And then this is also similar. So divisible by x minus 1. And then there's an invisible n minus 2. And then this is obviously just x minus 1. So we can say that this whole thing can be rewritten as x minus 1 times x minus 1 times whatever this expression is. So it's just x minus 1 squared times this messy expression. And then we are done, hence proved. Okay? So don't worry if you didn't see this clever manipulation about the n ones. But just remember that for x to the n minus 1, you can always see an invisible n right over here. And that's the key to the problem. And then also just group accordingly using the, I don't know, just move it over here in order to make it more convenient. Okay? Any other questions? Okay. Now, let's move on to the last topic of today's lecture. It's a little slow too. The neat thing about Miro is that you can actually use the mini map right over here. So you don't have to, I don't know why I'm scrolling. So like you don't have to scroll all over the place, right? You can just click. So the last thing is not really special factorizations. Again, I know the name, I named it like that, but this is actually a very useful strategy. Okay? So, let f of a be. So, just to clarify, multivariable factor theorem is just applicable for multivariable polynomials. What does this mean? It basically says it's not in terms of f of x only. It can be in terms of f of x, y, and there's also this closed form, like, I don't know, like that. Okay, so this is a multivariable polynomial. Okay, so let's recap this lemma. Not really recap, but let's introduce it. So let f of ab be a multivariable polynomial. So actually this also works for 3 variables, 4 variables, 5 variables, 1,600 variables. So it'll actually work. So let f of ab be a multivariable polynomial. If there it's just 2 variable, but as I said, it doesn't really matter how many variables there are. If there exists a polynomial single variable polynomial h of b, where f of h of b equals 0, then we can say that f of ab is equal to a minus h of b times q of ab, where q of ab is another multivariable polynomial with its degree less than f. So I know this definition might be a little confusing, but I hope that this next example will clear it up for you. It's not as hard as it seems. It's just a little extension of the one variable factor theorem, so like the standard factor theorem. Okay, so let's move on to a quick example if you don't understand what I said. So let's say we have f of abc is equal to ab squared minus a squared b plus bc squared minus b squared c plus a squared c minus ac squared. Okay? So you might think that you should factor the AB out of here and then factor the BC out of here. But I'm going to show you what you should do. So basically, you first look at the degree of the polynomial. So obviously there's this invisible one. So the degree, we use this convention deg, so deg. Degree of f is equal to 1 plus 2, so it's 3. Okay, so this is, if you forgot, you can recap it on like Khan Academy or something. So the degree of f is 3. So actually the fundamental theorem of algebra actually applies to this. So by the fundamental theorem of algebra, there are exactly 3 roots. Okay, so in fact, this fundamental theorem of algebra, it actually applies to multivariable polynomials. Okay, so this is the key here. So if you find 3 roots, that is basically it. You don't need to find any more. So if you find 4 roots or 5 roots, then there's obviously something wrong with your calculations. So what we're trying to do here is we're trying to find the 3 roots of this thing. So according to our example, let us try. I know this might be a little like random, but as you'll see, you just need a little bit of trial and error to figure out these roots. So let us say, or let us evaluate f of bbc. In other words, we're replacing all instances of a. I'll write this out. So replace all instances of a by h of b. So in this case, it's h of b equals b. So I'll do this in red. H of b equals b. Okay. F of bbc, what would this be? So there's this a right over here, is just a b times b squared, so b cubed. Minus this a is just a b, so b squared times b, negative b cubed. And then bc squared, bc squared minus b squared c, because it's not in terms of a, so it's just, we just leave it like that, plus a squared c. Oh, there's an a right over here, so b squared c. And then we see an a right over here, so minus b c squared. And then obviously this cancels, and then this cancels, and then just 0. So f of bbc is 0. And by the multivariable factor theorem, we can say that this is factored by a minus h of b, which is just a minus b is a factor of f of abc. So do you guys get what I did here? Okay. Don't be afraid to ask if you don't get a concept. Okay, good. So thus a minus b is a factor of this. So we have found one root. So the first root is a minus b. So we need to find the second and third. You can try to find this on your own, but I'll just find it for you here. We just replace, I know this actually might be a very familiar form. Yeah. So let's try. I'm seeing where I should have space. Okay, I think I have a space here. So let's try f of a cc. Usually for finding the roots, you have to try a lot of stuff. So basically, we're just saying h of b is c. Okay, so try f of acc. Technically, it's h of c. So f of acc, we get. Hold on. So ab squared, right? We have this ab squared. It's not in terms. It's in terms of a and b. So we have ac squared. I'll write the polynomial here. C squared and then ab squared. Okay, so I'll do this one and then I'll just say the third root. So a squared b, that's just a squared c, plus b, we have another b, so it's just c cubed because this b is a c, minus this b, so c squared c is just c cubed, plus a squared c minus a squared, ac squared. So bam, 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 and this is 0. So we can conclude that b minus h of c is just, technically it's h of b though. Sorry for the mistake. So b minus h of b is just b minus c. So b minus c is a second root. And then, so yeah, so like there's no really neat trick. You could use synthetic division to do all this. I have done it a couple times, but it's not very pretty because you have so many variables and you have to take care of all the constants and remainders. So I'll just suggest that you resort to the multivariable factor theorem. So as I said, it's just b minus c, and then the third root, I'll just say the third root is c minus a. So for this, if you were to try it out on your own, you would have to find that f of aba is 0, because we're replacing all instances of c with a. So just as a recap, we're just replacing all instances of a. So wherever a appears, you have to replace it with a b, and then wherever b appears, appears, you have to replace it with a C, and then C with A. Okay, so basically, we can say that this is equal to, careful, K times A minus B times B minus C times C minus A. Because we might have a coefficient right over here. So don't get tricked. If you find the 3 roots, you must also find the coefficients. You could plug in just like, I don't know, just plug in a lot of values for A, B, and C. Like preferably you could use, I don't know, A equals 3, B equals 2, and C equals 1. And then you would get K equals 1. Oops. Oh, yeah. K equals 1. So once you have found that coefficient, you have the complete factorization. So I'll actually recap it above here. So basically the first step is to determine the degree of polynomial. Thus, this finds the n roots, so number of roots. And then using multivariable factor theorem. So multivariable factor theorem, I'll just abbreviate it like that. Multivariable factor theorem, you would have to find the roots. Or actually, sorry, factors. Find the factors. And then after that, find the coefficient. You must not forget this step because it's very important. You can use a counter variable like k or a, preferably not a, so k or m or n, and then just solve for this. By plugging in values of a, b, c. So plug a, b, c, or like, I don't know, x, y, z, whatever your polynomial is. That's the key. So do these 3 steps, and then you can factor almost any multivariable polynomial. I know it's a bit tedious, but it's the best way, I guess. You should use this theorem most of the time. Okay, so now do this one. I'll just say it's not as hard as it looks. So it's not very hard. It looks hard, it's not very hard. So factor a plus b plus c cubed, and then all this. This is from intermediate algebra. Again, I credit Richard Russick for making this textbook available for us mathletes. So thank you. Also try this problem. Excuse me. So I'm assuming everyone has tried this. Yeah, so I know you guys might have tried something like this. So ABC, so that is f of ABC be this polynomial. So I know you guys might have tried, I don't know, this, or you could have tried something crazy like this, or anything else like that. But you might have found that this doesn't really work, doesn't exactly cancel all of this, these terms. So when you don't know what to do, you should always try 0 and 1. That's another strategy that you should know. So when in doubt, try 0 or 1. Okay, so basically if you're trying 0 as, I don't know, like let's say, take for example f of 0bc, you're basically saying that a is a factor of this, right? A minus h of b, h of, I think it's a, h of a, just a, right? So you're saying that a is a factor of that. So how should I say this? So you plug in 0 into the A or B or C. So actually, let's try that. So you will get, let's zoom out a bit. You will get let's just do it here. So f of 0 BC, you're replacing all instances of A with 0. It's very easy to do. So 0, just B plus C cubed minus B plus C minus A. Well, minus A is just 0, so cubed, plus C plus A, well, A is just 0, so sorry, it's minus C minus B cubed minus A0, so B minus C cubed. This cancels, and before you say that A is not a factor, note that this is actually B minus C, because negative of -1 times B minus C cubed is equal to, well, this negative goes out, and then you get 1 times B minus C cubed. And then you have B minus C cubed, and then that is just 0. Similarly, because these are all symmetric, this is a symmetric polynomial actually. So now you can similarly try f of I don't know, like f of A0C and f of AB0. And actually, I forgot the first step. You should always try. You should always figure out the degree. So the degree of f is 3. You can verify it here. Even if all these a cubed, b cubed, and c cubes cancel, you're still left with something like b squared c, and then that would still be 3. Okay, so you have 3 roots right over here. Now you can try this on your own, and then you'll eventually get that a, b, c are all roots of this ugly thing. So f of a, b, c is equal to k a, b, c. So don't get tricked by just finding the roots and just saying, oh, this is just a, b, c, because there's always this polynomial lurking out right there. And then f of a, b, c is very simple. You just to find the value of k, you just plug in simple values. For this one, I would like to plug in a equals b equals c equals 1. Okay, so that would give us, let's do it, f of 1, 1 is equal to 1 plus 1 plus 1 cubed, 27, minus, did I make a mistake here? 1 plus 1. Might have made a mistake here. Never mind, actually. So, minus 1, minus 1. So, this would give us 24. And then, that's for the left-hand side, right? The right-hand side is just k times 1 plus 1 times 1 times 1 is just k. So k is 24. And thus, f of ABC factored would get us 24 ABC. It's very simple. It's actually very simple for like an ugly expression like this. Usually, the easiest types of multivariable polynomials to factor are symmetric polynomials. So like, are they all in the same form or not? You could also take it like that. Now I actually, do I actually see another way to do this? You could actually use like, if you don't like all these ABCs, you can just x, y, z, and then adding them, and then x plus y plus z. It's a little more complicated, but you can also verify it like that. Okay. Okay. Yeah. So this is a trick question. Try to just think about it. It's not very hard. There's not really a strategy for this one. Okay. Since this is a trick question, I'll just cover it really quickly. Factor this A, B, C, A, B, E, A, C, D, blah, 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 blah. Before you try starting with a multivariable factor theorem and like finding the degree, like of course we can just say that degree of this thing is 3, right? And then you can try to use the multivariable factor theorem, but it'll get really messy. I tell you, it's gonna get really, really messy. Because look, this thing is in terms of f of A, B, C, D, E, F. It's a 6 variable polynomial, and it's not how you do it. So if you tried it that way, you should have thought that maybe there's an easier solution, and there is, because surprisingly, this is solved by SFFT. Simon's favorite factoring trick. Actually, not really. It's just grouping, I guess. Sorry, it's grouping. It's just grouping. So, AB times C plus C plus AD times C plus C. So I'm actually factoring 2 at a time. So, like that, like that, like that. And then BC, we can actually factor the BF. And then here you have the CF. So C plus C. Sorry, DF. C plus C. And then these C plus C's, you can just group them. C plus E times AB plus AD plus BF times DF. And then thus, this can be factored, right? Let me see. So, what's the F? Yeah. And then this is actually just A. Oh, oopsies. A plus F times B plus F. And then this is just C plus E. And then this can't be factored anymore. Okay, so this is kind of like a trick question. You should also, if nothing works, you should always try to find usual basics, because obviously for most in competition math, like there's like a lot of problems that that there's like this one AOPS solution that resorts to bash, but there's usually a slick trick. So this is just don't think too much, I guess. Note that this only works for AMC AIME problems. For Olympiad problems, you would sometimes have to bash. So, okay, so two more examples. So example 5.4, show that b minus c over a plus c minus a over b plus a minus b over c equals c minus b times a minus c times b minus a over abc. I just do the first step for you, okay? So multiply by abc to clear all the denominators. And then bc times b minus c. And then this, you can kind of form like a triangle right over here. So AC times C minus A plus AB times A minus B. This would, and the ABC, because you're multiplying by ABC, this would cancel, and then you get C minus B times A minus C and B minus A. And then up to this point, you really don't need to do so much work. You just need to verify that the left-hand side is equal to the right-hand side. This is very easy to do. You just need to find a degree. So obviously you can just expand for the first term, and then b squared c has degree 3. So you can also try expanding the other terms, but this degree of left-hand side is 3. And then degree of right-hand side is also 3. You see, it has 3 factors. So degree 3. I know I'm writing all over this, but degree of 3. Okay? Now, it's almost enough to verify that the left-hand side is right-hand side. But to be really sure, we have to try that these are actually all factors of this. So I'm not going to go into the details, but you can try. So it's just saying that try f of, let's just say f of ABC, okay? So f of replaces all instances of C with B. So A, B, B. And then try, this will just say try all instances of A with C. So C, B, C. And then this is just A, C. Okay? You can try this out. I encourage you to do so. This will all equal 0. Note that you should always use, you should use the left-hand side for this, okay? So that it will be a more formal explanation. And then after you do that, you can say that, okay, well, the left-hand side is just it's just equal to k times c minus b times a minus c times b minus a. And then plugging in like random values of a and abc is just, it gives you k equals 1, and thus we have the left-hand side equals right-hand side, okay? And thus this is proved. Okay, any questions? Any questions regarding to like this whole lecture? I have one more example. Okay, it's good that you enjoyed it. Thank you, because I put a lot of effort into making these examples. So this last example, I encourage you, I'll give you like 5 minutes to solve this. So last example will be from the Tournament of Towns. I don't know which year, it's just from the ALPS Intermediate Algebra textbook. So let A, B, C be complex numbers satisfying A plus B plus C plus D equals to their cubes. So the sum of the cubes, and then they're all equal to 0. So prove that the pair of the A, B, C, D must add up to 0. Okay? So that's a problem statement. Take 5 minutes to solve this. And if you're on YouTube, please pause and just try to solve it. Okay, so if you need a hint, note that this polynomial is symmetric, but I wouldn't recommend factoring this cubes thing. Okay, so I'll just say don't factor. Don't factor this cubes. The sum of, I mean, you could, but like it wouldn't. It's not the optimal solution. Okay, so it'll take like 1 more minute to solve. Yeah. I agree that this one was tricky. But I'll try to make it as simple as possible. This is a very good last example, so that I purposely put a hard example for you guys to solve. Okay, so let's just start with just comprehending the problems. Like we have complex numbers satisfying this, right? And then prove that a pair of the ABCD must add up to 0. So basically, we're just saying that all of the 4 choose 2 equals 6. 6, I guess, sums, right? So must add up to 0. So we're basically implying that A plus B is 0, B plus C is 0, C plus D is 0, A plus D is 0, B plus D is 0, A plus C is 0. That's what we're trying to prove. So we're trying to prove all 6 of these equations. So that's why it's so hard to do, right? What are we going to do? Well, we're going to try a little bit of manipulation, then we're going to try to actually do some factoring work. So let's move the, since these are equal to 0, we're going to move the B plus C plus D side sum to the right hand side. So we're going to get A equals B minus negative B minus C minus D, and then we're going to get A cubed, right? A cubed, because the sum of the cubes is also summing to 0. If you're wondering why I didn't even consider like letting A equals X plus Y, that's because it's gonna take a lot of time, and you're gonna set like a lot of variables, and it's gonna get really messy. So I don't want to do that. To be honest, this complex numbers, it doesn't really matter. So we have this, right? Now you see what we're gonna do. We're gonna cube both sides. So we have this, and then this is a negative, so we can pull out a negative right over here. Okay, so now A cubed. I'll make this in green. We have negatives, no more negatives. I think you see where we're going with this. Oopsies. Fun fact, this was also the last example problem, I think, from one of the sections in intermediate algebra. I forgot which, I think it was chapter 20, I forgot. Anyways, here you see this B plus C plus D cubed. I know it's kind of painful to expand this, but when you're in a competition, I guess you have to do it. So you might as well memorize it. Memorize the expansion of B plus C plus D cubed. It's gonna be worth it. So like we have this, the cubes, and then we have this 3b squared c plus 3bc squared, excuse me, 3 3c squared d plus 3cd squared, and then we have one more, so it's b and d. So 3 b squared d and 3bd squared. And then we have a extra 6bcd. Trust me on this. You can expand it out for yourself if you don't believe me. So we have this canceling with that, and then just 0. So this is just 0, and then equals to the sum of all those terms. Divide by 3. We can do so because you see there's a 6 right over here. So we're actually trying to factor this plus, what was it? I guess like that, and then like that. And then we have a 2abcd. 2abcd. I know this form is really, sorry, no a. So 2bcd. I know this form is really familiar to some of you. You might as well like factor it directly, but just because this is symmetric, I'll just do it for the sake of explaining it. Okay, so we try. You might not try this on the first try, but like I'll just try this directly. So replace all instances of b with negative c. So we can replace it with negative of a variable, and then you can replace it with a variable. You can also replace it with 1 and 0. And you can also replace it with anything else. But usually we would try these four substitutions. So try b equals negative c. So anything with b, we replace it with negative c. So b squared is just c squared. There's a negative right over here, but it doesn't really matter because it's squared. And then we have c cubed minus c cubed, because it's a negative c right over here. And then this is just minus cd squared. There's a negative, right? And then this is plus c squared d. Negatives, again, negatives squared is just positive. This is just c squared d plus c, actually this is minus because there is a negative. Actually, no, sorry about that. It's just directly c. And then minus 2 c squared d. If you don't see why, I'll just write it out for you. Okay, so basically, bam, bam, this is just c squared d, 2c squared d, bam, and it's just 0. Okay, so thus we can conclude that b plus c is a root. And then you can try the other two stuff, or roots, I mean, factors. So sorry, b plus c is a factor of this. Now, after trying stuff, you get b plus c times c plus d times b plus d is 0. Thus, one of these must be equal to 0. And that is enough to prove it. So basically we're just saying that b plus c is equal to 0, c plus d equals 0, and b plus d equals 0. So we're putting these OR, okay? This implies that a plus d equals 0, a plus b is 0, and a plus c is 0. And hence we have proved it. Because we get these statements from the original problem. Because it states that a plus b plus c plus d is 0. See? Right over here. Thus, from the factorization, we obtain these six sums, and we are done. Okay? So thank you guys for watching. If are there any other questions like regarding this whole lecture? Let me check Discord. Yes? Okay. Yeah. Thank you. Yes. Math is very fun. It's a lot of beautiful stuff. Also, you guys, it's kind of, I know this is kind of an advertisement, but you can find me at ALPS. So at, sorry. If you want to, so this is my username on ALPS. So this is my ALPS username, okay? Yeah, so you can friend me on there. I know this was kind of off topic, but yeah. So we have covered today's schedule, and I hope you guys really enjoyed it. Thank you guys for attending, and I'll see you next time. Actually, this might be my last lecture on GSHOC. So it has been a pleasure for working with you guys. So thank you, and goodbye.